Hello and welcome to Students Teach Teachers. I assume if you're watching this video, you have suffered amnesia because of your students' academic dishonesty and have completely forgotten Newton's third law. If that isn't the case, this video is not for you. If this does apply, keep watching and you might remember something. Sorry. To begin, you need to know what a force is. A force is an interaction that is always part of a mutual action that involves another force.
What Newton's third law states is that every action has an equal and opposite reaction. Whenever an object exerts a force on another object, that other object is exerting the same amount of force back to the first object in an opposite direction. These forces always occur on different objects.
Basically, what Newton means is whenever two objects interact with each other, a pair of forces will be acting on the two objects that are interacting. These forces will always come in pairs, and they are called action and reaction forces, which are equal and opposite to each other.
Let's say you're playing whack-a-mole, and with your hammer, you manage to hit a mole.
She's really good.
What do you think is stopping the hammer and making it bounce back to you?
I'm guessing the mole.
Exactly. The hammer whacks the mole, and the mole whacks the hammer.
But what exactly is the action force and which one is the reaction force? They both look the same to me.
It doesn't matter. The only important thing is that they can't exist without the other. If you don't have an action force, you don't have a reaction force at all.
So if you and I were to push the same object in opposite directions and equal magnitude, would both forces we apply be action and reaction forces?
Actually, no. Although the forces are opposing each other, they are acting on the same object. Therefore, they are not part of the same system and are both action forces. In this case, the action and reaction forces will be pushing the object and the object pushing me, and you pushing the object and the object pushing you.
So basically what you're saying is that nothing ever moves because there is always a force equal in magnitude and opposite direction, making the net force zero? No, not zero. Zero. What? How is that similar? What?
No, you see, this law is studied in a system, which is a portion of the physical universe that it's chosen to study the changes that take place within it. The forces within a system will cancel out. Therefore, to move a system, you need a force from an external system, which is another system apart from the one that you are studying. Since the force is from an external system, the forces will not cancel out and the object will move. Only the forces that act on an object contribute to the motion of the object, not the forces it is applying on other objects.
Examples! Yay! Ew. Did you know that when you are swimming, you are experiencing Newton's third law firsthand? You push the water backwards, and the water pushes you forward. This law is the reason why fish can swim, and birds can fly. It is present all around us, non-stop. But I don't know how to swim.
Okay, well, then suppose you're playing with your cousin and you fire a Nerf gun. When the bullet is fired, it exerts the force on the gun and it pushes it back. You're witnessing Newton's third law.
But if the forces are equal and opposite, why doesn't the gun accelerate back just as fast as the bullet? Like, it's logical, right?
The bullet's acceleration will be greater than the gun's because it is less massive. Since the Nerf gun is more massive, more force is needed to get it to accelerate the same as the bullet. Remember Newton's second law where it states that acceleration is inversely proportional to an object's mass?
I don't know. I feel my memory coming back to me slowly.
Well, the object's mass will affect the acceleration, but the force will still be the same. This explains why when you jump or walk, you won't feel or see the Earth's acceleration towards you, but it is still there. The Earth is so massive and the acceleration is so minuscule that it is negligible.
Okay. Chow, can you provide another example? I still don't get this whole system thing.
Let's say you're taking your baby sister on a walk, and you're pulling her along in a toy car. If she tries to push the car to get it to move from the inside, do you think she'll be able to move forward?
Oh, I know this. Okay, no, the car will shake, but it won't move.
Exactly, the car's pushing back just as hard as your sister's pushing forward. It wouldn't work because the forces inside of a system cancel each other out. In this case, your sister and the car are the system. If she wants the car to move forward, you have to move it by pulling it. This way you're exerting a force on the car and the car is exerting a force on you.
And the car will move forward when you exert more force on the ground than the force you are using to pull on the car. Once the car is moving, the only thing you need to do to keep it moving is to apply just enough force to offset the friction force between the wheels and the ground.
So, me and the car are a system, and me and the ground are another system.
Exactly. Since the force exerted by the ground is from an external system to me and the toy car will move and the net force will be non-zero.
Okay. So according to Newton's third law of motion, if Mr. Manuel is sitting on the chair and I try to pull him while I'm standing up, I won't be able to. Because Mr. Manuel will pull on me just as hard as I pull on him, and the forces will cancel out.
Technically, yes and no. You are on the right path, but you are wrong. Where you were wrong is that you didn't take friction into consideration. Friction is the force that resists motion when the surface of one object comes in contact with the surface of another. When you pulled Manuel towards you, Manuel pulled you towards him. But since you are standing, you push on the floor and exert an action force, and the floor pushes you, exerting a reaction force. The same thing happens with Manuel. The wheels on his chair push on the floor, and the floor pushes on his wheels. Since the force of friction is greater between your feet and the floor will exert a greater reaction force on your feet.
This means you will be able to stay at rest and pull Manuel towards you, because the friction between the wheels on Manuel's chair is less, which means there is less of an opposition to motion between the wheels and the ground.
Wait, I remember now. Me and Manuel did a similar explanation in class. Newton's third law. Interaction between objects, two pairs of forces, equal in my... it all makes sense. Yay, my amnesia is cured. Hooray.